Okay, so good morning, everyone, and happy Wednesday. We just did our camera test, and I hope that now it's clear what is required of you. And please, again, I don't wish to inconvenience anybody, especially over the web like this, over Zoom like this. But starting on Friday, when we're going to have our first quiz, I will require you to have such a configuration. Otherwise, I won't be able to accept your quiz. And yeah. Okay, so as usual, I'm going to write what we're going to do at first on the board as our objectives. And you will see that today we have a very rich set of things to discuss. In some sense, the things that we're going to discuss today are going to provide us with the theoretical framework of what we're going to do in the rest of the semester. And for that reason, I would like us to understand these notions. So we're going to do many examples. And we're going to discuss linear combinations, the notion of linear dependence and independence, the notion of basis and dimension. And finally, we're going to discuss the notion of a subspace, which is, again, is going to be central for the rest of our course. So in some sense, if we were to prioritize the importance of the lectures that we're going to have from this point forward, this would be somewhere on the top. So please pay attention. Please ask the questions that may occur to you as this happens. So yes, there will be a recording that will be posted and you will be able to review it as many times as you like, but I think it is invaluable to actually ask your questions during the lecture. And as we said before, you most probably do everybody a favor. Many people are going to have the same question that you have. It's subspace. I'm so sorry. Yeah, this is the word subspace. You will see my E. For some reason I do it like this. So my apologies for my handwriting. Okay, but that says subspace. Okay, so let me do it like this so that everybody can see it. Okay, thank you. So and I think there was one more question here that I don't want to ignore. So the word linear, very good. I mean, we're talking about linear algebra, linear, and so on and so forth. Simply speaking, the easiest way that I can answer this question is that is the mere absence of higher powers. So you don't see squares, third powers, square roots, sines, cosines, and things like this. So everything is in terms of first order, first degree expressions of the independent of the variables that we're going to examine. So you will not see squares, you will not see third powers, and so on. That's what linear refers to. Okay, in a very concrete sense, if you like. Okay, so let me remind you our setup. So we said that we're going to study vector spaces. So imagine that you have a vector space V is a vector space. And when I say it's a real vector space, which means that we scale by real numbers. As you're going to see later in the course, there is a possibility that we scale by complex numbers, or much later in the course by coefficients belonging to a finite field. But for the moment being, and for the majority of the things that we're going to do in this course, we're going to work with real vector spaces, which means that if you give me two vectors, I can assign to them their sum. So we have a sum. If you give me a real number and a vector, I can scale the vector by the real number. These are the two things that we can do. Okay, so this is our premise, this is our setup, and let's see what we do with this. So if U1, U2, up to UN belong to V, and lambda 1, lambda 2, lambda n are real numbers, then the expression lambda 1 U1 plus lambda 2 U2 plus all the way lambda n UN is called a linear combination of the vectors U1, U2 up to UN. Okay, this is called the linear combination of these vectors. So let's give an example. So let's say that we are in R4 and U1 is 1, 3, 2, negative 1. U2 is 1, 1, 0, negative 3. And U3 is 2, negative 1, negative 2, 0. Then the vector 2U1 minus 3U2 plus U3, meaning when I say plus U3, it's the same thing as saying plus 1 times U3, which is going to be equal to what? Let's see if we can do it from memory. So it's going to be 2 minus 3, that's negative 1, plus 2, that's 1. And then 6, so 2 times 3 is 6, second coordinates now. 2 times 3 is 6, minus 3, that's 3, minus 1, that's 2. And third coordinates now, 2 times 2 is 4, minus 3 times 0 is 4, minus 2, that's 2. And last coordinates, negative 2 plus 9 is 7. So this vector is a linear combination of the vectors U1, U2, and U3. What's the significance of linear combinations? There's more than one can say in one statement, but basically you can use the vectors that take part in the linear combination in order to express the vector that is the linear combination. You said you asked where are you subtracting from? What do you mean by that? The numbers 2, negative 3, and 1 that I used as coefficients were pretty much chosen arbitrarily. So my lambdas, if you like, so lambda 1 is 2, lambda 2 is negative 3, and lambda 3 would be the number 1. They were just chosen arbitrarily. So what do you mean when you're saying subtracting from? This is not a t here. This is the number 4, right? This is the number 4. And that means that we have 4 places for our real numbers, 4 coordinates. Okay? Any more questions, please?
Wait, can you explain what that 4 means again?
Yeah, R4, when we write R4, means the quadruples of numbers. So literally speaking, R4 really means R cross R cross R cross R 4 times, which means that it consists of all vectors that have 4 numbers as their coordinates. Okay, that's what R4 is. So last time we introduced the vector space Rn. We showed what the operations in Rn are. No, these are not 4 elements. It's 1 element. So this is 1 vector. This is a second vector. This is a third vector. And each vector is a quadruple of 4 numbers. Okay? In the same way that in R3, in the same way that in Calc 3, you were looking at vectors that had, let's say, a 3D vector looked like what in Calc 3? Or something like this, 3, -1, 2. See how you have 3 coordinates, 3 components, 3, -1, and 2. Here, the only difference is that I don't use diamond brackets. And I also use that T, this T right here, which means what? It means transposition. We said that in Rn, we really want to use column vectors. And instead of having to write column vectors, so I could have written U1 as 1, 3, 2, -1. Do you see how much harder it is to work with those things? I indeed, as you're going to see later, want them to be column vectors. But in order to make our life easier, we write them as rows. We put that T, which means that they really are column vectors, and also the commas to again make our life easier. Okay? No, R4 does not mean a vector of 4 real numbers. It is the set of all vectors of 4 real numbers that consist of 4 real numbers. Okay, so R4 is not just 1 vector. It's the totality of those vectors that have 4 coordinates. How did we calculate? So you need, so look, for example, how we found 1, right? You need to multiply this number by 2. So in other words, in the first coordinate, you would have had 2 times 1, which is the first coordinate of the first vector, minus 3 times 1, because the first coordinate of the second vector is again 1, as you can see here, plus the number 2, which is the first coordinate of the last vector. And then you do this for all 3 coordinates, for all 4 coordinates. Okay, and that's how you get 1 here. So if you were to do it for the second number, that would give you what? It would give you 2 times 3, because 3 is the second coordinate of the first vector, minus 3 times 1, which is the second coordinate of the second vector, plus -1, which is the second coordinate of the third vector. Okay, why don't we do an example? Why don't I give you an example so that you can do it yourselves? So in R3, let U1 be 3, 1, -5, and U2 be a vector space is a set consisting of vectors. That's correct. 2, -1, 3. And that's why I said that it's a good idea to go over the first lecture and possibly keep some notes on what a vector space is. So if you look at the definition that we gave last time, you will see that a vector space is a set consisting of elements that we called vectors. And we can do two things with those two vectors. We can add them and we can scale them. And there were 8 properties that underlined what those operations between the vectors behave like. So here, could you please compute 2u1 minus 4u3 minus 4u2? Could you please go ahead and compute this? Okay, just to make sure that we understand how we do, how we find linear combinations in Rn. If you can do it for 3 coordinates, you can do it for 4, for 5. I doubt that we will ever see, you will see that in our course. I think the highest that we will ever go is 5 coordinates. I don't think we will ever see anything larger than that. Okay, let's see if we did it right. For the first coordinate, we have 4 times 3, which is 6, minus 4 times 2, so minus 8. 6 minus 8 is negative 2. For the second coordinate, we have 2 times 1, which is 2, minus 4 times negative 1, so 2 plus 4, that's 6. And for the last coordinate, we have 2 times negative 5, which is negative 10, minus 4 times 3, minus 12. So negative 10 minus 12, that's negative 22. And that's it, right? Sure. So it's 2 times 3, 1, negative 5, minus 4 times 2, negative 1, 3. If you want, you can do the multiplications first. So you can do 6, 2, negative 10, plus negative 8, 4, negative 12. And then you need to add them up, and you will get minus 2, 6, and negative 22. Okay, and now you have it in full detail. Any more questions, please? So this is called a linear combination. And pretty much we're going to be dealing with linear combinations throughout the semester. And let me remind you what we said on Monday. We said that when you try to solve a system, so solving the system, so somebody tells you solve the system 2x minus y plus 3z is equal to 4. X plus 2y minus 4z is equal to 1. And 3x plus 3y minus z is equal to 7. So let's say that somebody asks you to solve this system. This system, as we said, is pretty much the same thing, the exact same thing, as you can rewrite it as x times the vector 2, 1, 3 plus y times the vector negative 1, 2, 3 plus z times the vector 3, 4, 3, negative 4, negative 1 is equal to 4, 1, 7. Okay, so solving this system is the same thing as asking is the vector 4, 1, 7 a linear combination of 2, 1, 3, negative 1, 2, 3, and 3, negative 4, negative 1. And with what coefficients? So do you see how something that you have already seen enough of, like a vector, I'm sorry, a system, all of a sudden can be expressed in the language of vector spaces, and specifically by using the notion of linear combinations. Okay, this is very, very important. So let me leave it like that for a second so that it resonates with you. Questions, please. Questions. Okay, so most of the things that we're going to do today hinge on the notion of linear combinations. So it's all about linear combinations, and I would like to make to give you some idea here, because it might not be immediately visible. Why isn't anything a linear combination of anything else? And here's the reason. Let's work in R3, in the three-dimensional space. And you may ask, if I give you two vectors, right? So I give you two vectors. Here's one vector, u1, and here's another vector, u2. And I'm asking you, what is the condition for if I give you a third vector, v, so that the vector v is a linear combination of u1 and u2? Does anybody know the answer to this? Possibly from Calc 3? When do you think I will be able to write v as a linear combination of u1 and u2? Anybody tell me? No, it doesn't necessarily have to do with projections, actually. At least in any way that I can think of here. Or maybe maybe it does, actually, in some sense. So I think there is a way to be able to justify it using projections. But what I'm looking for here is this. The two vectors that I'm giving you form a plane, right? They're two line segments. They emanate from the same point. They form a plane, right? It's this parallelogram and everything that it extends to. That's a plane. For the vector v to be a linear combination of u1 and u2, it has to belong to the plane that is created, but that is spanned, as we say, by u1 and u2. So v is a linear combination of u1 and u2 if and only if it lies in the plane spanned by u1 and u2. Okay. And you know, here I'm interpreting the vector space geometrically, and I will have the luxury of doing this for 2 and 3 dimensional vector spaces. But I want you to understand that this intuition is lost the moment you go over to like much higher dimensions. Even at dimension 4, you cannot start drawing things, even though people still draw things in dimension 4, and they find a way to do it. But you know, it's certainly not a realistic way. It's not a way that imitates reality. Okay.
It's a question, excuse me, if is a un is such as minus U, so this will be in the same plane too.
Yeah,
This
yeah.
will
I
be
mean,
applied
it
like that.
doesn't right. So when you take linear combinations, at least for two vectors, everything that you generate through linear combinations will lie in the same plane. Doesn't matter whether it's positive or negative. Yeah.
Thank you.
Whether the coefficients, in other words, are positive or negative. In fact, you do need positive and negative coefficients in order to cover all possible directions. So yeah, so that's the notion of linear combination. And now I would like to turn my attention to dependence and independence. So again, our setup here is that of a vector space. So let V be a vector space. And like I said before, when you hear that, because I know that some of you are having trouble, at least now, when you hear a vector space, you're like, oh, what do you mean? I mean Rn. And if you're having trouble with Rn, think of R3. Think of R3. Okay, so make it that concrete in your mind. So let V be a vector space. And let U1, U2, up to UN be vectors in V. Then U1, U2 up to UN are called linearly independent when none of them is a linear combination of the remaining ones. They will be called linearly dependent if at least one of them is a linear combination of the remaining ones. And what I wrote down is the exact negation of what it means for the vectors to be linearly independent. So this means i.e. when they're not linearly independent. So if you give me a bunch of vectors, they can be two things, either linearly dependent or linearly independent. Please understand, we will do examples in a second, but for generic examples, it's not that easy right away if I give you a bunch of vectors to realize whether they're linearly dependent or independent. But as we're going to see, we're going to develop methods that will allow us to do this quite effectively. Not today, but we will get there. In every vector space, you can have vectors that are independent and vectors that are dependent. And we're going to give examples right now. Okay? Okay. So let's give some examples. Let's work with the simplest vector space that we can, R2. Let's work in R2. Let me give you two vectors that are not linearly independent. So in R2, the vectors 1, 0 and 0, 1 are linearly independent. Why? What would it mean for two vectors to be linearly dependent? It would mean that one of them can be written as a linear combination of the other one. What do I mean by linear combination of one vector? Can anybody tell me what can I possibly mean by linear combination of one vector? So linear combination of one vector is simply a scalar multiple of that vector. So basically what I'm asking is, can I write 1, 0 as some number lambda, which I don't know what it is, maybe you can tell me what it is, times 0, 1? Can I do that? Can you see how you can do it or why you cannot do it? Why can't you do this? You cannot do this because when you multiply out, exactly, that's exactly the reason why. Because you will never be able to get, you will always get 0 on the second coordinate. You can never get 1. So 1, 0 is not a linear combination of 0, 1. And similarly, 0, 1 is not a linear combination of 1, 0 for the same reason. So 0, 1 and 1, 0 are linearly independent. On the other hand, 2, 3 and 6, 9 are linearly dependent. Can you see why? So basically, to have them linearly dependent, one of them needs to be written as a linear combination of the other two. Can you see how that is possible?
Because
How is it-
lambda is 3. Yes.
So you can write, exactly. So you can write, for example, 2, 3 as 1/3 of 6, 9. And that means that they're linearly dependent. Yeah, you could also write 6, 9 as 3 times 2, 3. It's the same thing. So one of them is a scalar multiple of the other.
So, sorry to interrupt. So, in other words, if we can derive a value for a possible lambda, then in that case, then they are dependent.
Yeah, of course. That's what it means.
Thanks.
Let me give you a different example. Let's make it a little more interesting. Let's work in R3 now. I will give you a bunch of two bunches of 3 vectors. And I want you to try to figure out, I'll give you a couple of minutes, if they are linearly dependent or independent. You will have possibly you will have to answer 2 different questions, in other words. So here's are the first vectors. 3, 4, 6 is the first one. 2, 0, 0 is the second one. And 0, 2, 3 is the third one. So Are they linearly dependent or independent? Can you find one of them, which is a linear combination of the other two? And here's the second one. 1, 0, 0, 0, 0, 3, 0, negative 2, 0. So can you answer the following question? Is it possible for each of these three vectors to find at least one of them, at least one? Nobody tells you to do it for everyone, right? Can you find at least one of them, which is a linear combination of the other two this time? This time, remember, in the definition, it said of the remaining ones. Since we have three vectors, we're looking at the other two. Okay, so give it a try. I'll give you a couple of minutes. Okay, so let's try to do this together. Okay, so we have to ask if 3, 4, 6, for example, let's start with 3, 4, 6. If it doesn't work, then we can go with 2, 0, 0, and then with 0 to 3. But let's start with 3, 4, 6. And ask if 3, 4, 6, oops, I'm sorry. Is a linear combination of 2, 0, 0. So I could put lambda and nu. But you know what? Since eventually these are going to be unknown numbers, I might as well put x and y. So is it x times 2, 0, 0 plus y times 0 to 3? So that's what we would like to see. Can we find x and y so that this is true? Okay. I'm so sorry. My system kicked me out, so we had a technical problem. I hope it happens sometimes. So can somebody please tell me what were the 3 first vectors so that I can go back to the solution?
3, 4, 6, and 2, 0, 0, and 0, 2, 3.
Okay, so as I was saying, we would have 3, 4, 6 is x times 2, 0, 0 plus y times 0 to 3. So we're asking, is the first one a linear combination of the other two, right? Which translates to what? 3 will have to be 2x plus 0y, meaning 2x. And 4 would have to be 0x plus 2y. And 6 would have to be 0x plus 3y. Do we all agree that these are the conditions that we should have? And let me explain this even more, because the first vector is 2x, 0, 0. This is what happens when you multiply by x, when you scale by x. The second vector is 0, 2y, 3y. So the whole thing would be 2x, 2y, 3y. Hence, you get these equations right here. So the first equation implies that x is 3, right? The second equation implies that 2 is y, that y is 2. The hard thing now is to make sure that the third equation works. And the third equation does work. So y is equal to 2 from the third equation. It does work. So we just found our numbers, right? So we just found that 3, 4, 6 is the same thing.
Why is x equal to 3 in the first one?
No, I'm sorry. I meant, yeah, you're absolutely right. I meant 3 halves. So we're going to have 3 halves of 2 zeros times 2, 0, 0 plus 2 times 0 to 3. So they are linearly dependent. They are linearly dependent. Then, what were the other vectors that I gave you? Could you please, somebody tell me the second set of vectors that I gave you?
1, 0, 0,
1, 0, 0.
0, 0, 3,
Mm-hmm.
0, negative 2, 0.
Okay, so if I try, for example, to get the first one and write it as x times 0, 0, 3 plus y times 0, negative 2, 0. And let's see what I get. I get 0, 0, 3x plus 0, negative 2y, 0. So pretty much this is the same thing as 0, negative 2y, 3x, right? Then the system that I'm getting is that the very first equation is that 1 is equal to 0. I shouldn't even make an attempt to go any further. 1 is equal to 0 is impossible. So the first vector cannot be written as a linear combination of the other two. Does this mean that they're linearly independent? Does that mean that they're linearly independent?
No.
No, I have to try the other two, right? So I have to try if 0, 0, 3 now is a linear combination of the first one and the last one. And guess what? I will find the same thing here. I will find that it's impossible for the same reason. And then I should try whether 0, negative 2, 0 is a linear combination of the first one and the second one. And again, the answer will be no for the very same reason. So what is the answer? They are linearly independent. They are linearly independent. And the question that, so any questions, first of all, for the solutions of these two problems?
So it means they don't locate it in the same plane?
Like I said before, I mean, for R3, yes, it means that there is no plane that contains all three of them. But please realize that for other cases, it might not translate to planes when you go to higher dimensions. For this dimension, that means exactly what you said. It means that there is not a single plane that contains these three vectors. Yeah, that's exactly what it means.
Thank you.
Sure. Whereas there is a plane that contains these three vectors because they were linearly dependent. But that is specific to the case of three vectors in R3. You will not be able to express it using planes in other dimensions. For other dimensions, we actually have the notion of hyperplanes, which would have been something similar, but we're not going to do it. The question that
Another stupid question. Another stupid question. If you say R3, it means XYZ. But if you say it looks like R4 or 5, what do you refer these R4 or 5 to? So
when I say
X and Y
R4,
and Z.
when I say R4, then the vectors would have looked different. They would have had 4 coordinates. If I had said they're R5, then the vectors would have had 5 coordinates. Okay?
Thank you.
All right. So the question that needs to be addressed here is it possible that we give a definition that allows us to do the whole thing at once without having to check one vector at a time? And the answer is yes. And it is as follows. U1 up to U2, U1, U2 up to UN are linearly independent if the equation x1 times u1 plus x2 times u2 plus xn times un equal to the 0 vector only has the solution x1 is equal to x2 is equal to xn is equal to 0. So the only linear combination of those vectors that you can make equal to 0 is the obvious one, when you take all the coefficients equal to 0. Otherwise, if one can find x1, x2 up to xn with not all of them equal to 0, not all of them being non-zero, I'm sorry, being 0, so that x1 u1 plus x2 u2 plus xn un is equal to 0, then u1, u2, un are linearly dependent. So in other words, for linearly independent vectors, no linear combination of them can be 0 unless all the coefficients are 0. I repeat, no linear combination. So for linearly independent, let's write it down. For linearly independent vectors, no linear combination of these vectors can be 0 unless all the coefficients are 0. So, for example, I gave you a moment ago the vectors 1, 0, 0, 0, 0, 3, and 0, 0, negative 2. So let's see how else I could have done it. So if I took 1, 0, 0, 0, 0, negative 3, and 0, 2, 0, and I took a combination of them, and I set it equal to the 0 vector, let's see what this would give us. It would give us x0, 0 plus 0, 0, negative 3y plus 0, 2z, 0 is equal to 0, 0, 0. Which means what? This means that, let's add them all together, x, comma, 2z, comma, negative 3y has to be equal to 0, 0, 0. Which means that x has to be equal to 0, 2z has to be equal to 0, and negative 3y has to be equal to 0, which means that x is 0, y is 0, and z is 0. Right? That means that all the coefficients have to be 0, which means that the three vectors are linearly independent. So that's a nice way that you can do it, so that you can avoid to have to do three things at a time. Questions, please. Otherwise, if
It's
yeah,
n.
sorry, if
It-
one can find, otherwise, if one can find x1, x2 up to xn with not all of them being 0, so that the corresponding linear combination is 0, then they are linearly dependent. Okay. So why don't we take a break for 5 minutes, and then we will continue when we come back. Okay, so we'll come back, everyone. And let me ask if we have any questions so far.
I think there's some questions in the chat.
Oh, there are. Okay, let me take a look. The quizzes are not open notes, and that's why I need you to have the cameras. The quiz is going to be about 10 minutes, and the quiz is going to be, we are going to start them on Friday. Okay. First quiz will be on Friday. I think it's going to be a quiz on linear dependence and independence. And also a homework assignment has been posted for you, which is due on Friday. So we will have the chance of discussing it on Friday morning if you have any questions for me. I remind you that the optional assignment, which is about the procedures for this class, is due tonight. Okay. A few of you have already completed that. I would encourage everyone to complete it. Okay. Any more questions? Okay, sorry, I was, no, I'm sorry, you couldn't hear because I was, yeah, there is homework, and the problems that we're doing today, if you can understand them, you will be fine for Friday, okay? That's why I keep saying, please review the problems that we do in class. So the next thing that I would like to discuss is the notion of a basis. So if V is a vector space, then the vectors u1 up to un form a basis of V if we have two conditions. Every vector in V is a linear combination of U1 up to UN. And secondly, U1 up to UN are linearly independent. Sometimes, so this is the definition of what it means to have a basis. Sometimes we say that for the first condition, that U1 up to UN span or generate the space V. So what does it mean for a bunch of vectors to span or generate the space V? It means that their span is, it means that every vector in that space is a linear combination of those vectors. So let me give the standard example that is useful to know. In R3, the vectors 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 1 form a basis. Please remember that these vectors were heavily used in linear algebra. I'm sorry, in Calc 3, we even had a special names for them. Do you remember what their names were in Calc 3 for these three vectors? Remember, we called them I, J, and K. Okay, so these were the vectors I, J, and K. Form a basis. Form a basis. Why? If I give you any vector, ABC, then any vector ABC can be written as A times 1, 0, 0, plus B times 0, 1, 0, plus C times 0, 0, 1. And if you ever tried to write a linear combination of them equal to 0, you would simply get all the coefficients right away to be 0. Then this would imply right away that x, y, z is 0, i.e. they're linearly independent. And here that means that they span R3. There was a question about generation and spanning. Let me see what it was. The space V, the underlying vector space V. Yeah. So I can do the same thing in Rn. Can you guess what the vectors are going to look like in Rn? In Rn, we have the basis. Consisting of the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay, and this is called the standard basis. This is called the standard basis. Okay. Now, every space, every vector space that has a basis consisting of finitely many vectors is called the finite dimensional space. Every vector space that has a basis consisting of finitely many vectors is called finite dimension. In this course, we're going to study just finite dimensional vector spaces. Finite dimensional. So Rn is finite dimensional. Any two bases in a finite dimensional space have the same amount of vectors. So this means that you cannot have in the same space a basis that has 10 vectors and another basis that has 7 vectors. That's impossible. And that common number, this common amount, is called the dimension of the vector space. So Rn has dimension n. So R2 has dimension 2, R3 has dimension 3, R4 has dimension 4, and so on and so forth. Any questions so far, please?
Is it possible one of these two bases be positive, finite positive, and the other one finite negative, or it is should to be the same?
As we're going to see, every vector space which has dimension at least 1 has infinitely many bases. So yes, they can be anything you like. Okay, they can consist, the coordinates of the vectors can be positive, negative, zeros, anything you like. In fact, here's how it works. If V has dimension n, then any n linearly independent vectors form a basis. So if you can find 3 linearly independent vectors in R3, they're a basis automatically. If you can find 4 linearly independent vectors in R4, if you come across 4 linearly independent vectors in R4, they're a basis, no questions asked. Same thing with generation. So if V has dimension n. And is generated by V1, V2, up to Vn, then they form a basis. So in other words, the conditions for forming a basis are two, right? What are the conditions? That the vectors are linearly independent and that every vector is a linear combination of those vectors. But if you know the dimension of your space and you have the right amount of vectors, so for example, you are in R4 and you have 4 vectors. To know that those 4 vectors form a basis, you need to check only one property, either that they're linearly independent or that they generate the space. Okay, so our life will be very easy when we work with Rn. The question is, what else are we going to work other than Rn? And here's the last thing that I would like to introduce for today. Okay, so we're not going to just work with Rn. We're going to also work inside Rn. So a vector space is not a basis. A basis is a bunch of vectors inside the vector space that generated and are linearly independent. Okay, so R4 has the standard basis, and it also has infinitely many other bases. As I said a moment ago, every vector space, if it has dimension at least 1, it has infinitely many bases. So a basis is a set of a few vectors. The vector space is a very large infinite set consisting of vectors. Okay? So a vector space is not equal to a basis. It has a basis. Right? So the last notion for today is the notion of a subspace. So if V is a vector space and U is a non-empty subset, is a subset of V non-empty, then U is called the subspace if it is closed under the operations. What does that mean? It means if U1 and U2 belong to U, then their sum belongs to U. If U belongs to U and lambda is any number, then the scalar multiple of lambda with U belongs to U. Then it's called the subspace. So in our course, we're going to deal with Rn and its subspaces. In our course, we will deal with Rn and its subspaces. So for example, geometrically speaking, a subspace in R3, geometrically, it's going to be either the whole thing or it's going to be a plane that goes through the origin, or it's going to be a line that goes through the origin, or it's going to be the vector space, the subspace consisting only of the vector 0. So I repeat, in R3, you can have either the whole space, that's a subspace, or a plane that goes through the origin, or a line that goes through the origin, or the origin itself. That's called the zero subspace. Okay, so in general, the central problem that we're going to face is if a subspace is described to us using some description, using some method, how can you find the basis of a subspace? So the central problem in this course is to find the basis and thus determine the dimension of a subspace. So central problem in this course. And when I say central problem, I mean as a direction of developing the material in this course. It's not like I'm going to ask you to do it today. Central problem, how to find a basis and thus the dimension of a given subspace of Rn. That will be one of the central questions in this course. Now, let me go over a little the homework that I have already posted for you for next time, and let's see what it involves. So for your first homework, I'm giving you two vectors, 1 and -1. Let me discuss them a little. Let me give you a couple of hints. It's the first homework, right? 1, -1, and 1, 1. And I'm asking you, are they linearly independent or not? Basically, what you have to do is take an equation, a linear combination of them, and set it equal to the 0 vector, and try to see if x, y can be non-zero. If you can figure out that this equation is satisfied by non-zero x and y, then they're linearly dependent. If they're the only x, y's that satisfy these equations are 0, then they have to be linearly independent. Number 2 says show that the vectors 1, 0, 0, 1, 1, 0, and 1, 1, 1 form a basis of R3. Okay. Well, they are the right number. There are 3 of them. So all they need to do is, for example, be linearly independent. So do the same thing. Take a linear combination of them. And set it equal to 0, 0. I mean, you will have to work it out. So this will be x plus y plus z, comma, y plus z, comma, z is equal to 0, 0, right? Which translates to x plus y plus z equal to 0, y plus z equal to 0, and z equal to 0. And see, I mean, I practically solved the problem for you. Can this be satisfied for anything else other than 0, 0, 0? And you will see that, no, it's not. And last one says, suppose that the vectors 1, 2, -1, 0, and 1, 3, 2, 0 span the subspace U. What do we mean by span? We mean we take all linear combinations of these vectors. So U consists of all the linear combinations of these vectors. I'm asking, is the vector 1, 1, 0 in U. This is what I'm asking. Meaning, what I'm asking is, can you write the vector 1, 1, 1, 0 as a linear combination of the first vector and the second vector? Can you do that? Can you solve this system? Give it a try. Okay, this is a description for the 3 problems that form your homework for Friday. Okay, I wish you, let me actually take our attendance. I'm sorry, I forgot to take our attendance. I'm going to take the attendance every single time by asking you to type a keyword on the chat. Okay, so please everybody add the keyword independence on the chat for everyone, Just write the word independence and enjoy the rest of your day. I remind you that my office hours are at 11:50 in 10 minutes from now, in case you would like to ask me anything. Okay, I wish you a great rest of your day. I will see you on Friday with our first quiz, where I'm going to ask you if a bunch of vectors are linearly dependent or independent. That's going to be our first quiz. Is a bunch of vectors linearly dependent or independent? Okay? That will be all. Have a great rest of your day.